I have here the compound 1-chloro-2-iodo-cyclohexane. Let's figure out our stereochemistry for these points. These are two chiral centers. We can see that because we have two wedges sticking out of this cyclohexane, this is going to have stereoisomers. So first, I can look at my iodine complex. Now I've started it this way so that we can do this a little more quickly. Both my hydrogens are hidden, they're pointed to the back, so I'm not going to need to do any flipping around here. I've got iodine comparing with carbon, comparing with carbon. Clearly iodine is number one. This carbon is connected to a chlorine, a hidden hydrogen, and a carbon here. This carbon is connected to two hydrogens and a carbon here. So this is carbon, hydrogen, hydrogen. This one is carbon, hydrogen, chlorine. So therefore that carbon wins. So this is my number 2, and then this is my number 3. So I'm going clockwise. That means that this is R stereocentered. So let's put that on there. We've got an R orientation. Now the chlorine, let's erase this stuff. Now for the chlorine side, chlorine is clearly going to be number 1. My carbon here versus my carbon here, well, this carbon is connected to an iodine, well, this one is just connected to another carbon. So this is going to be my number 2, this is my number 3. So I'm going reverse order. So this would be sinister, going to the left. So this would be the S orientation. How many stereoisomers could I have of this molecule? Well, since I have two chiral centers, I could theoretically just have each one switch. So let's start with drawing another one where I've got the S version of the iodo. Well, that's going to be pretty simple because that just means that I'm switching the I and the hydrogen. So if I switch those two, then my iodine is going backwards. My chlorine is still coming forwards. Then I'm going to have So I'm going to have a chlorine here, iodine here. Chlorine stayed the same, so it is still going to be in the S orientation. The iodine switched, so now this is going to be in the S orientation. So there we go. Okay. How about another one? Let's switch my chlorine now. So now my chlorine is facing backwards. My iodine is facing backwards. Chlorine here, my iodine here, and now iodine is still S, just like it was here. Chlorine just became R. All right, last one. My iodine is going to flip back forward. So now my iodine is R, and my chlorine is R. So if I were to name each of these, saying that my chloro is my number 1 carbon, then I would say 1s, 2r. So I'd write this as, first one, let's just go in order, 1s, 2r, 1-chloro, 2-iodo-cyclohexane. This one, well, they're both s's, so the second one would be 1s, 2s, 1-chloro, 2-iodo-cyclohexane. Third one, 1r, 2s, 1-chloro, 2-iodo-cyclohexane, and the last one is 1r, 2r, 1-chloro, 2-iodo-cyclohexane. There we go. We have 4 distinct enantiomers, 4 distinct chiral molecules that are all slightly different from each other. But let's adjust this. What if instead of an iodine, these were just 2 chlorines? Let's look at what would happen here. Now, because switching chlorine out, or switching iodine out for chlorine is still a much higher atomic number than the carbons around it. It's at 17 versus 6. That orientation is still going to stay the same. All of these are still going to be R, S, S, and R. Okay? However, I want you to notice something. In this point where they're both facing forward, what if I took this molecule and just turned it around? What would happen to these two chlorines? Still the same molecule. But if I turn it around, then I would actually get this orientation. Notice that. I take my R here, my S here, and I just turned it around. It's the same orientation. So when two of these are the same, one of their enantiomers is actually still the same molecule. So let's change this name to reflect that. So this is now 1,2-dichlorocyclohexane. So the S and the R's are referring to either one of the chlorines. So when I have 1S, 2R, well, which chlorine is which? I don't know. When I have 1R, 2S, which chlorine is which? So when I have this orientation like this, where I can flip this back and forth and it's still the same molecule, even though it looks like they're different enantiomers of one another, I'm going to have what we call a meso compound. Meso compounds. Meso compounds can be more quickly determined than writing out every single possible enantiomer by looking for an internal plane of symmetry. If a molecule has an internal plane of symmetry where I can just reflect this side onto the other side, it has a meso compound. Okay? So we're going to need to be able to identify enantiomers of a compound, identifying all of the possible enantiomers of 2 or 3 stereocenters. And we're going to need to be able to identify when they have meso compounds by looking for this internal plane of symmetry. So here I've got another example, this time a straight chain that is going to have a meso compound. So this is pentane 2,4-diol. So we've got a pentane with 2 hydroxyl groups sticking off of it. Both are facing forward. So I can see that if I just took this out of the page and flipped it around, I would still have an enantiomer. So once again, I've set this up so that our hidden hydrogens are the group facing backwards so that we don't have to worry about any of the flipping around. And so if I look at this and I number the priorities here, we've got oxygen versus carbon. Carbon, oxygen, clearly going to beat that. So my oxygen will have the priority. Number 1, I've got a carbon here that is connected to 3 hydrogens, all having the atomic number 1. And I've got a carbon here that is connected to another carbon and 2 hydrogens. So carbon, hydrogen, hydrogen, which is 6, 1, 1. 6, 1, 1 beats 1, 1, 1. So this would be priority number 2. And this is 3. So I'm going around clockwise. That means that this is going to be R, the R orientation. Okay? Let's use a different color to show that. There you go. It's a little more apparent. So then this one here, it's going to be the same thing, just in reverse. This is going to be my number 1 group. This will be my number 2 group, and this will be my number 3. So I'm going around counterclockwise. That will make this the S orientation. So if I write this out, my first enantiomer, this would be 2 and 4, 2R, 4S. All right? So if I'm going to make the meso compound of this, I would draw this like so. So here I've got my flipped orientation. Now this time my hydroxyl groups are facing into the board. So let's go ahead and put in our hidden hydrogens so that we can figure out what our actual orientation here is. So if we number these, my oxygens are still going to be number 1, hydrogens are still going to be number 4, and my carbons are going to be the same, 2, 2, and 3. Okay? And now in order to figure this out, I need to flip these two. So I would flip the 1 and the 4 groups So now I'm going to erase this and put a 1 there. And so I go 1, 2, 3. That's going to the right, which is R. But because I flipped them, this would be S. This is now the S orientation. So it's flipped of that one, R to S. Okay, good. Now the same thing for this one. I flip this 1 and this 4, make that a 1. And I'm going in the reverse. I'm going to the left. That would be S. But since I flipped it, this would be the R orientation. So I should be able to see that I could really number this carbon chain from either direction. It's going to be the same thing. 1, 2 hydroxyl, 3, 4 hydroxyl. Or 1, 2 hydroxyl, 3, 4 hydroxyl. So either way, it's the exact same compound. So the 2R4S and the 2S4R are the exact same compound. Okay? So they are meso compounds. I could draw the other two enantiomers of this, and I will. So I would have one looking like this, where now my hydroxyl group on the left is facing out. I could have one more where my hydroxyl group on the right is facing out. So then this would give me the R orientation. This would give me the R orientation. This would give me the S, and this would give me the S. So I can see I really have 3 enantiomers of this compound instead of 4. So we're going to need to be able to identify these meso compounds by identifying that it has that internal plane of symmetry. If I just draw a dotted line straight down the middle of the molecule, I can see that they are reflections of one another.